Hey folks, just putting out a quick tweet and then I'm gonna... Oh, okay, I have my mic down already. I felt like my mic was still up. One sec. Alright. So, I'm not going to, spend... Oh wait, let me make sure this isn't gonna fall asleep and then I'll get straight to it. I'm still on a two computer setup since I don't have a second monitor yet. Um, do do. Um, mm, okay, we're good. So, let me put this away. Here's the beginning of the quick little math talk. So this came from a conversation I had with Abner Coimbray, and it occurred to me that, I had recently learned some things that had always frustrated me that I didn't know them, and he was expressing a similar frustration. And so I started trying to explain it to him there, but I decided to hold off on it because it's kind of a lengthy topic. I mean, it's not extraordinarily long the way I'm going to present it now, um, but it's still a bit long. It's still it takes some time to think through exactly the way to put it forward. And the full thing is, like, if you wanted to really, really get down to the nuts and bolts of it and build it up from very first principles, it would take even longer than that. Now, I also want to give credit where credit's due. None of these are my ideas. I got this all from Introductory Real Analysis, this book here. I got it from Dover Publications. They have a lot of great math books, and I read these, for my education and recreational enjoyment of math stuff. So that's the source for this information, and I just want to share it because I was debating whether or not to actually put this out there, because I'm not really like someone who does legitimately try to actually explain math stuff for reals. I've done it a couple times, and I don't think I'm like particularly good at it, but the problem is with this particular topic, I did a quick survey, and there's just no good version. There's no version that even has the right information, so that I can find easily. So even though I'm not presenting it as cleanly and sharply as other people, I'm at least putting the right information out there for the people who happen to watch my videos and are interested in this. So, what exactly is the topic? The topic is defining a real number. And this is, like most sort of abstract mathematics, almost completely useless if your reason for studying math is to, like, program games or something. It's much more interesting if you just enjoy the rigorousness of math and you lament the fact that the definition of real numbers that you've heard don't sound rigorous. The real definition of real number kind of fixes that a little bit. I mean, completely, it's totally rigorous, but it satisfies that kind of annoyance that you might feel if you care about that kind of thing. If not, then this whole thing will seem completely like useless application of mathematical approach to answering questions that you don't have. But then this video isn't really for you if that's all there is to it. So why is this an issue? What are the why do we need a definition for a real number, right? Part of the problem is it's so fundamental, it feels obvious that if I just give you a poor definition, it'll feel like that is good enough anyway. But if you're trying to build a mathematical concept out of first principles, right, like from simpler things that you're already convinced of all the time, without just appealing to the idea that you already know what a real number is, that this continuum where all the possible values exist, whatever that means. What are all the possible values? How do you define and analyze operations and things on all the possible values? What is that? What we really want, if we're trying to be super rigorous, is something that lets us define it out of something simpler that we know completely, right? That we have good definitions and analysis for. So the way we do this for other things is not as hard to see. In fact, there's good content out there about this. So, for instance, if you take natural numbers, let me do a little digression here. If we take natural numbers as granted, right, and we would have to go just one step farther down to like axiomatic set theory to actually get how we get natural numbers. But if we just take them as a thing that we understand, 1, 2, 3, 4, 5, and so on, and that's the natural numbers, we can add them together, and we always get another natural number, right? We can multiply them, and we always get a natural number. But they have a whole bunch of limitations. They're missing 0. You can't always subtract 2 of them and get another natural number. You can't always divide them and get a natural number. Stuff like that, right? So if we take these as something that we will use as an axiom, I think that that is a solid grounding that almost everyone can agree on. Now, like I said, this isn't the full Monty. If you wanted to know how you build this all the way out of first principles, you'd want to get a book like this one, where they'll go down to even more basic axioms and get there in an even more detailed way. I'm just going to take axioms that I think we are all feeling solid on for now, but you can always go, deeper. This is just the axiom I want to start with because it gives you the intuition about how these definitions are supposed to work and when they're being helpful and not just nonsense, right? So if that's our natural numbers, how do we get integers? Well, we basically get integers by saying I want to close my number set on the operation of subtraction, right? In other words, when I say I want to close my number set, what I mean is I have the set of numbers here, natural numbers, and it's possible to take two natural numbers and subtract them and get something that's not in that set. I want a new set of numbers that's closed under that operation, so that whenever I subtract two things from my number set, I get another thing that's in my number set. And another part of this is you don't want to kick the can down the road. You don't want to have a thing where I say, alright, well, I'm going to define a set where all of these things have a subtraction. So there's a special thing for 1 minus 2, and a special thing for 1 minus 3, and a special thing for 2 minus 4, and so on. You want to have a set that once you take something out of that set and apply it to it goes back into itself, so that you don't have to keep on going another step further, so that you are continuously closing, like pseudo-closing, like this set has answers for the previous set but not for itself. We want a set where within this set, if I take things out of the integers and subtract them, I should get integers still. I shouldn't have to add yet another set on top of it to get more subtraction answers, right? So closure doesn't just mean adding answers to questions we don't have. It fundamentally means making a new set that has a property that the previous one didn't have, but retains all the properties that the previous one did have too. So if I'm closing this set under the operation of subtraction, how do I go about doing that? Well, you could just say like, well, we have negative numbers, right? 1 minus 2, and that's negative 1, and there you go. It's closed now because we have negative numbers. But if we want to be a little bit more fundamental about it, right? like using just as few assumptions about what we already know about about negatives as possible, what we can actually do is say let's have this thing that we'll call like a representative of an integer, and we'll call it like a1, a2, and so this will be our integer representative. And what we can do is say that they're all the operations we want, so addition and multiplication, which we already have in this set, right, as well as subtraction, which we're trying to get. We'll define them all in a way where if we do any of those operations on a pair of these things, we get a new one, right? And there we go. We'll have a set of integer representatives that are closed under subtraction, and we'll be pretty close to what we want. So how do we do this? Well, I'll skip all the details. This is something you might want to study more on your own if you are interested, but for subtraction in particular, let's take a look at that one, because that's the one we're trying to close under. And hopefully you can imagine how you would do the other ones. Addition and multiplication you can figure out separately, right? So what we'll do is we'll say this representative minus this representative is defined as the thing you get when you take, let me make sure I do this right, a1 plus b2 and a2 plus b1. Alright? So that's sort of arbitrary and weird looking, right? What is that happening? Why are we swapping these? Why addition and we're just making one? But let's set that aside for a minute. We'll figure out why that's happening. But do you agree with me, because hopefully you do, that this here is defined in the terms of real natural numbers. So if a1 and a2 are natural numbers, and if b1 and b2 are natural numbers, then all of these, a1 plus b2, a2 plus b1, that's only using addition. We already said we had addition. So this thing must be a pair of natural numbers too. So hopefully you can see that whatever this new thing we've created here is, it's a set of things which is in fact closed under this operation that we just defined, right? So we've got closure under subtraction out of the way. Now, why does this make sense? Well, if we take any pair of representatives here and think about them as being a1 minus a2 minus b1 minus b2. Now, here we're assuming that a1 and a2 can't be natural numbers anymore. These must be integers because we're subtracting them and assuming we get a result. So this isn't rigorous. This is just intuitive, okay? But if this is how we write our pair, then we can see that what we're talking about is this is the pair that you get when you do a1 minus a2. And that's what this pair means. But we can't say that this is a1 minus a2 because if these are natural numbers, then this might not be defined. This pair is just some arbitrary pair, but this might not be defined, right? So this is the non-rigorous way of looking at it. But if we rewrite this now, then we would see that, well, okay, we're getting a1, that's a negative, b2 is positive, so plus b2 minus, alright, let's see, a2 is negative and b1 is negative, so a2 minus b1 or plus b1, right? So you can see here, this is where the a1 plus b2 and a2 plus b1 come from. It's that we choose to define it this way because this is the thing we actually are talking about when we talk about integers. Right? This has the same structure as this under subtraction. So, if you agree that this is how integers work, then it turns out that these pairs are just a goofy way of writing down integers, right? And furthermore, if we want to get from integer representatives, which is what these things are, to actual integers, what we want to do is just say, well, there are certain pairs that look different, but that are actually the same. And let me give you an example of that. Say we took 3 and 4, and the pair, we'll let that be A, and say we have the pair 5 and 6, right? These two pairs look different, 3, 4, and 5, 6. They are not the same pair. But it does seem that if we're trying to use these as 3 minus 4 and 5 minus 6, those should be the same if we're talking about integers. So that's why these are only integer representatives. What is an integer? An integer is the set of all of the pairs that is equal, right? So for instance, here, if we say that these are equal, well, what are we saying? Well, to be rigorous about it, we're saying that A1, A2 is equals B1, B2 if, and now we're going to only use things that real numbers can do. We're not going to appeal to integers anymore. We're going to just use or naturals, right? Sorry, my bad. We're only going to do things that natural numbers can do because we are being rigorous, not intuitive this time. We want this to be something that we are defining in terms of stuff we already know is solid. So when are these two things equal? Well, I can't just say when this is true, because if I say when this is true, now I'm doing that thing where I subtract, and I can't subtract natural numbers and guarantee I get a result. But what I could do instead is I could say this. Why can I say this? Well, because first of all, I'm only using addition on each side, right? And so that is closed under the natural number. The natural numbers is closed under addition. And on top of that, not only is it legal to say this, but it's also the thing we mean by integers, right? So 3, 4, 5, 6 becomes 3 plus 6 and 4 plus 5. Hey, those are equal. And so that's how we get that these are equal. And if you, study this a little bit, explore it for yourself, you'll find that, any integer you can pick a bunch of pairs, an infinite number of pairs that represent that integer. And for the purposes of defining the integer is that whole set of the pairs that are equal. And so -1 is the special name in the integer set, is the special name we give to that set of integer representatives that are equal to these pairs, and in general that have the property that this is one bigger than this, right? Alright, I'm going to take a quick moment to check the chat, make sure that I haven't gone totally crazy. Oh, looks like we have no chat activity. That's fine. Then I can keep going, uninterrupted. Let me double check I'm actually streaming. Oh, yeah, we're streaming. Alright, onward then. So that's, hopefully you've seen something like this before. I'm just giving you the basics so you have this idea in your head if you've never seen it before. But this is not meant to be anything new, right? We can do the same thing to get from integers to rationals. So I won't go into full, this level of detail with rationals. Instead, I'll just say, what is the thing we're trying to do when we make rationals? We're trying to make them out of integers. What are we trying to do? Well, we're basically saying I want to close my number set on the operation, I should say under the operation of division, right? Because you have this thing with integers where, some things you can divide. This is just like with natural numbers. You can subtract some natural numbers and still get a natural number. You can divide some integers and still get an integer. But if you ask, what is 1 divided by 2, then you're back into a situation where you're getting a thing that you want to have an answer to. You want your set to be closed under the division operation, and yet you are finding a pair where it's not. And so how do we proceed? Well, we proceed in basically the same way. We make rational number representations, which are just pairs. We define, operations on them, such as, well, let me do it this way. A1, A2 divided by B1, B2 is the pair, let me make sure I get it right, A1 times B2, I'll write it this way, and A2 times B1, right? We have an equality system, A1, A2 equals B1, B2 if A1 times B2 equals A2 times B1. And again, you should also check that all of the other operations are still preserved. Uh-oh, I'm getting a phone call. Let me silence my phone real quick. I meant to do that. my bad. So, again, you should confirm that all the other operations can be defined in such a way that you preserve the properties of the integers when you go to the rationals. You should also confirm that this definition of equality between rationals corresponds to your intuition about how rationals work, and so on. Alright, now we're going to get to reals, right? Because this is what this video is really meant to be about. How do we really define a real number? And as you've seen before, we're kind of trying to build something out of previous things that allows us to only use operations that we know are solid, that have good definitions. And this is where the problem I have with a lot of the stuff that's out there arises, because when you try to define a real number, a lot of people, like on casual mathematics videos and stuff, will throw out ideas like the following as definitions of real numbers. Anything you can plot on the real number, on the number line, right? These are my examples of definitions that aren't solid. I would say rigorous, but I don't know how to spell it. I just realized, so I'm gonna, dodge that issue. Anyway, so anything you can plot on the real number line. That's a definition I see on a lot of the sort of casual math stuff. What does that mean? Anything you can plot on, or maybe any point, right? Anything / any point you can plot on the number line. The problem with this is it doesn't, first of all, give us any kind of way to analyze, like, what are the operations? Like, is addition just you measure distances from 0? How are you using a ruler? Why are we using a ruler in mathematics? Why can't we deduce these things from non-pictorial representations of them? That's the way that everything else has worked so far, is we can define, rigorous, clean definitions of what these things are, and all of a sudden we can't do that? Why? Why are we putting points down and measuring them? That's not a good definition, right? Hopefully you can see that that's not the same level of solidness that the previous definitions were. It's some kind of, like, oh, if you can plot it, it's a real number, but how do I work with that, right? How do I generate examples of them? How do I add them together, multiply them together? Why am I even convinced that I know what all the real numbers look like? Do I have a set of all real numbers? What is that like? What do they look like? Because I mean, here's a problem. If I draw a picture, any points I put down on the number line is got some width to it, right? So it's not just covering the real number; it's also covering certain rationals, and the rationals are already, dense enough that you can take any two rationals, and there's an infinite number of them between those two rationals you picked. So I could just say that the rationals are any number on the number line, right? I mean, we know we have proofs that there are numbers that aren't rational, but why do I even care? Why shouldn't the number line just be the set of rationals? It doesn't make a lot of sense, right? It's not rigorous. Another one that I see is kind of like a variation of this, which is, and this one I'm not going to say is totally wrong, partly because I just don't understand it, and it looks a little bit more real in the sense that there are people who propose this and give it a name and say that it's useful. I don't understand it personally, so I can't comment on it too much, besides to say that it doesn't satisfy my standard of rigor that I feel like I should be able to satisfy given how rigorous these two definitions are, and that's this idea of a Dedekind. Oh, I might be spelling that wrong. Cut? And the idea here is that it's not just a point on the number line, but it's like the infinitely small point, and it's like that gap there, the set that you get when you take all the numbers less than this point here, and all the gaps in between, all the rational numbers and all the gaps in between them, and you can tell if two things are equal if the set underneath them is equal, right? And one real number is less than another real number if if its set is less than the other subset. So it's starting to sound kind of like a definition where we're not just saying it's a point, but it's like, no, it's something about there's a set of things less than this, and if those are subsets of each other, then if one is a subset of the other but not vice versa, that gives some kind of ordering on them. So there's some semblance of like defining this out of first principles, but I still don't know how do I add them, how do I multiply them. And maybe these have good answers, but they don't feel quite as good as these did, the rationals and the integers. So I'm going to take the approach that I have up here and try to build a structure that we can define operations on and test equality between that are representatives, right? We're going to build real number representatives, and we will then say that a real number is the set of all real number representatives that are equivalent to each other, in the same way that we have before. So first of all, let me kind of lay the foundation, just like I did with these. What are we closing our set under? I've set up this pattern. Hopefully you've detected that I've set up a pattern. You should be ready for me to pay off. I've got a spelling correction on the chat. It's two E's, not two I's. That does sound right. So I want to close my number set under limits, is basically what it boils down to. Thank you, Juan, for the spelling correction. So what do I mean by this? Well, first of all, we're going to have to do a few things carefully and precisely. First of all, by limit, I mean the precise delta epsilon version, and that's why I have these fancy symbols down here. I'm talking about the fancy delta epsilon definition. Right. If you're not familiar with that, I'm not going to fully review it right now, but the idea is kind of, given an arbitrary closeness defined by epsilon that you want your value of your function to get to, there should be some delta you can set that says whenever x is within this delta, the epsilon is met, so that you can make your range get closer and closer to a limit point. Like you can say that my limit is equal to whatever. As epsilon gets closer and closer to 0, I'm making a smaller and smaller neighborhood around that value of the limit, and there should be a neighborhood of x's getting closer and closer to each other too. Alright, so with that in mind, we have to look at what is why is this a problem? Does this problem exist? Are the rationals not closed under limits already? And furthermore, what is a limit operation? Because previously we were talking about operations of pairs. A limit is kind of an operation on like a series of numbers, right? So I said I wasn't going to go too far into delta epsilon, but I will give you an idea of what kind of thing we have to take a limit on. In the most general sense, a limit is on like a series. So it's not just A1, A2, it's also A3, A4, and so on. It goes all the way up. Every natural number, there is some index in this series, right, for that natural number. So A1000 has an element is an element in this series, right? And so now we're not doing an operation on a pair, we're doing an operation on an infinite series. And that operation is this limit thing. Now the other thing that we're going to want to be careful about here is that not all infinite series are a valid infinite series for a limit, right? Previously, each pair, we were saying any pair should be a pair I can do this operation on, and I want this to be closed under that. When we say we want to be closed under limits, that doesn't mean that all infinite series should converge according to the delta epsilon definition. So how do we be precise about this? Because if not all series are going to converge, even when we've closed our set under limits, what are we actually doing that we don't already have, right? We want some kind of definition of what series should converge that doesn't in the rationals, right? If I can show you a series in the rationals that should converge but doesn't, then we have some kind of intuitive basis for why we need real numbers. But what are the definitions for this? What is should converge? So first of all, let me give you an example of something that shouldn't converge. Say my series is like 1, 0, 1, 0, and so on, like that forever. This is one that, for now, I know we could talk about crazy ideas of infinite sums or something weird. For now, we're going to say that this does not converge, especially not under the definition that we're talking about, the delta epsilon definition of a limit. This is a non-convergent series, clearly. I could also give you an example of something that definitely does converge. Let's take the series 1 half, 1 half, 1 half, 1 half, and so on. That definitely converges on 1 half, right? So, great. We have an example of a convergent thing and a non-convergent thing. They're both built out of rationals, so we're not adding anything new. What is an example of something that feels like this series that should converge, but doesn't converge for whatever weird reason? Well, this series will be a little bit hard for me to write down, but maybe I can do it. Let me pull up a calculator and try to do this. Okay, so here's how I'm going to first give you the algorithm I'm using to generate the symbols, so that you're convinced I could do this indefinitely, so that for every nth, for any natural number, there's an index into this series that you could look it up if you just iterated this algorithm for long enough, and therefore the series is in fact a series of rational numbers. And the way we're going to do this is we're going to do a sort of series of like bisections of a range. So we're going to start with the range 1 to 2, right? The range from the rational number 1 to the rational number 2. And then we'll say at each step we're going to bisect the range, taking the point right in the middle of it. And this is the next element of the series. Okay? So for instance here, if I bisect this range, I get 3 over 2, or 1.5 is the next element of my series. Great. So then what do I do? Next I'm going to take that number, I'm going to call this x. How about? We're going to square x. Okay? So I'm going to take 1.5 and I'm going to square it. Right? And then what we're going to do is, if x is greater than 2, update the range to the lower number to x, right? Else, if x is, aka, x is less than or equal to 2, right? I'm going to write this kind of like code because I'm a programmer. What can I do? Update the range to x to upper, right? And so now we have a thing where we start with a range, we bisect it, and then we test it against some criteria. Is it square greater than 2? Then we take this range where we're saying, all right, too big, shrink it down. Otherwise, too small, increase it, right? This is just like any binary search, except we're doing it over an infinitely dense set of points. And if you're thinking this through, what are we searching for here? We're searching for the square root of 2, right? So let me explain why, and then we'll iterate this out a few times, and then we'll explain what the point of all this is. How do I know I'm looking for the square root of 2 with this bisection algorithm? Well, at each step I'm picking something in the middle, right? I take x and I square it. Now, if that were to equal 2, if x squared equaled 2, then x must be the square root of 2, right? So if x is greater than 2, I'm saying, all right, that's too big. I'm looking for something in the range between lower and x. My value isn't x, it's too big. And we already said it's not 1, right? We started with a range between 1 and 2 because we know the square root of 2 is somewhere in between these. So it must be somewhere between lower and x, right? And similarly, if it was too small, then we do this. Now, at each step, what I have will always be a rational number. Why? Because we started with a rational number here and here, and every time we bisect it, we're just getting a rational number, right? How do I know that? The bisection is just the sum of those two rational numbers divided by 2. Rational numbers are closed under all those operations, right? I can add two rationals and get a rational. I can divide a rational by 2 and get a rational. So at each step, I'm getting more and more rationals. I never hit something irrational in the entire series. So, let's see. If I'm now going between 1 and 1.5, then let's bisect that. 1 plus 1.5 divided by 2. 1.25. If I wanted that as a fraction, that's 5 over 4, right? Okay, now let's square that. Square. So that squared is much less than 2. I've gone too small now. So now my lower is 1.25 and my upper is 1.5. So 1.25 plus 1.5 divided by 2. Alright, 1.375. That's something to do with 8. So let me think this through. There we go, 11/8. Right? And so I'm somewhere between, let's see, 1.25, right? And 1.375. Okay, let's bisect it. Okay, this is something to do with 16. How many sixteenths? 21. Okay, 21 sixteenths, and so on, right? Hopefully you agree with me that I can do this indefinitely, so for any point in this, any n in this series, I can find out what the rational number is there. So this is a series of rational numbers. And if it's converging on a rational number, what would we have found? Well, that would mean that according to this, right, delta epsilon sort of definition, there's some rational number such that no matter how far you go along this series here, or rather I should say there's some rational number such that you can get arbitrarily close to that rational number by picking an n far enough along in this series to, technically I shouldn't actually have said a delta epsilon definition. This is kind of like more like an n epsilon because I'm using a series. That was my bad. Don't worry about this too much. I got that detail wrong. Someone will have to do a better video than me. Anyway, I just realized that delta epsilon is for functions, and this is on a series. It's a different thing. Point is, if I want to get arbitrarily close to whatever number this converges on, I should be able to set epsilon super close to 0 and say where is the n where all of the points after this are within that x plus, or let's say that y is what this converges on, right? The limit of this equals y, right? Then if y is a rational number, that means that there's some number such that we can get arbitrarily close to it in this series. You know, there's some n where all the points after that in the series are within epsilon of y. Okay. Now, if this were possible, what we would find is that that number squared should be equal to 2, right? Now, forgive me, I'm going to skip the exact way we can get around doing that. Basically, the idea is if this, if each of these squared, is getting closer and closer to 2, then I don't really need to skip it. Okay, let's just look at it this way. Let's look at this series squared, right? 9/4, 25 16ths, and so on. Y squared, right? You agree with me that if I square all of these elements, then we're just going to get arbitrarily close to whatever the square of the limit is, hopefully. And what that means is that these are getting arbitrarily close to 2 now, and this y squared must be a rational number that when squared is equal to 2, which we know is impossible. It's a bit hand-wavy, but hopefully that's enough to convince you, right? So what we have here is a series that looks kind of like this one, where it's getting closer to a value. Well, this one isn't really getting closer, it's just always a particular value. Maybe I should throw in one other kind of convergent series just to make sure we're like fully on the up and up here, giving you a good impression of how this works. Right, so there's a series that is converging in the standard sense, not just it's all 1/2, but in the standard sense it's converging on the number 1, and no two elements in the series are equal to each other. Okay, same thing here, no two elements are equal, but they're getting closer and closer to some number, something, but that thing they're getting closer to isn't a rational number. So this is what I mean by the idea that there's some kind of sense under which the rationals aren't closed under a limit, but there isn't really a rigorous definition here even yet, because how do I know which series should be closed, right? I have an example of one that feels like it should be closed, but feels like isn't a particularly good metric, right? It's not a particularly good rule. So what is the good rule? Well, I'm going to introduce you to this concept of a Cauchy sequence, which basically means it's not a sequence that converges on something. It doesn't have to converge on something, because as we see, this doesn't converge on a rational number. But this is a Cauchy sequence, as are this and this. This is a sequence where, given any epsilon, let me grab my epsilon here, there is an n such that for any m, I'll say like 1, or like, well, m r greater than n, right? So greater than or equal to n. So for any pair m r greater than or equal to n, the absolute value of am minus ar, remember, if these are indexes, so n is an index into the series, these are two indexes into the series, so I'm taking two elements out of the series past a certain point. Is less than the epsilon, right? So in other words, if I want to say, give me, show me that you can get as close to each other as 1/1,000,000th, right? My epsilon is 1/1,000,000th. I'm saying, show me a point in the series where every pair after that point have a distance less than 1/1,000,000th from each other. And this doesn't actually require that the series converge on something. It just kind of requires that the points be getting closer and closer to one another, right? And this is well defined on the rationals, right? You can give me a rational epsilon, and I can look at this series and say, oh yeah, it is the case that there is a point here after which all of the in this series after which all of the elements in this series are within that epsilon, right? And I don't at any point have to say, but there's this weird situation where it looks like it converged, but it doesn't. No, it looks like it converge. It looks like it converges really means that the points are getting closer to each other in this sense. Okay? Again, that's not the full Monty. It's a little bit hand-wavy, but hopefully that's enough to satisfy a cursory version of this kind of question of how do I define a real number. So, the idea of closing under limits, what we really mean by close under limits, or what I really mean by close under limits, is that we want a set of numbers where every Cauchy sequence converges. I might be spelling that wrong too. If Juan is still in the chat, he might tell me. Let me see. Uh-oh. I might have lost the chat. I want to double check because don't want to get that kind of thing wrong. We want a set of numbers where every Cauchy sequence converges to a number in the set, right? That's what I mean by closed under limits. So anytime I have a series where the points are getting closer and closer to each other, that should also be a sequence that converges to something in my set. That's the idea. So our definition for a real number is going to look kind of goofy because unlike before, I can't use a finite number of rationals, but I shouldn't expect that to be able to because we're going from countable infinity to uncountable infinity. It's not surprising that that a little bit of infinity has to work its way into the definition as well, right? So if I have a series like this that is a Cauchy sequence, then it is a representative for a real number. Now, like before, there can be lots and lots of sequences that all are representatives for the same number. In fact, before there used to be a countably infinite number of representatives for each thing. Now there are an uncountably infinite number of representatives for each real number. But that's not a problem, right? We're still saying here are our representatives, and it turns out if you look at these definitions and you are familiar with how a limit works, then we can take a plus b as if those are two real numbers, take a representative from each set, right? And then we'll just say that this is a1 plus b1, a2 plus b2, a3 plus b3, and so on. And so if both of these are Cauchy sequences, it turns out that this one will have to be. Forgive me, I'm skipping the proof. I'm leaving some of this to you. Now that you have the definitions and concepts, hopefully these things won't actually be that hard for you to fully grasp on your own. So if those are both Cauchy sequences, then this is a Cauchy sequence. Furthermore, if we said that this converged on a real and that this converged on a real, then we can find out what the sum of those two reals are by finding out which real this converges on, right? Now, this can feel still a little unsatisfying because unlike before, we can't write down the full representative. We can't do the full operation. We can't write down the full addition and all that. But most of the time when we're dealing with reals, what we end up having to do is kind of tricks like this, where we find some sequence according to a finite size definition of that sequence, right? So we never need to actually deal with the full infinity of the sequence. We just have some definition that lets us know what